Hello and welcome to Psych 319, Chapter 14, Part 1. If I'm lucky, there'll only be one part to this lecture here. Just a reminder that there are several important things that need to be done by the end of the semester. You need to complete your rough draft for your individual project and upload it to Blackboard by 5/16. Late submissions will not receive feedback, and you know that's important for your success. All other work besides the final quiz, the final lab, and the final draft of the paper are due on this day as well. I'm not going to grade late submissions. I need enough time to give you my full attention when grading the final papers. The final draft of the paper is due on the 20th. No late submissions will be accepted. Take a look at your syllabus regarding this policy. Also note that 5/20 is not a Monday. I'm going to need the weekend to grade your papers because your grades will be due very soon after your finals. So pay close attention to these dates, write them in your calendar. Then the final exam will be between 6 and 11 on Monday, May 23rd. Hopefully there won't be any blackboard problems, but I've given us a day just in case. Again, see the syllabus. There's no makeups. Your lowest score is dropped automatically, and even if you're doing well in the class, you still need to take the final exam. And it's kind of a just-in-case policy. You know, if everybody else in the class does really, really well, your grade could go down, even if you're doing well going into the final. All right, so we're going to talk about a new process here, decision-making. And again, while this seems intuitively similar to problem-solving and reasoning, we've learned that reasoning is a very formal method of problem-solving, and decision-making also has a very formal definition as well. So there are actually three distinct processes. And you can see the poor kitty cat here needs to rethink a decision because it operated on a very short-term desire to be up the tree, and it didn't really fully think about the consequences of coming down the tree. So we make decisions every day. A deliberated decision is something that has either high cost or uncertainty, so we tend to take more time with it. This is unlike problem solving or reasoning where you use logic. You can use logic and so on and so forth in problem solving. These are not totally mutually exclusive, but decision making tends to involve very long-term goals. And we typically use our everyday life experience to make decisions. These are called heuristics, rather than using mathematical rules or so on and so forth. So we rely on these kind of biases to guide us through our everyday decision making. And these aren't always the best thing, the most accurate way to proceed about things. Most of the time heuristics works, which is why we use them. They're very quick and dirty tricks to help you make a decision, but you'll soon see that there are actually a lot of problems associated with using and relying on heuristics. So when we make decisions, we make them based on a belief. The outcome of the decision has consequences. They can be good or bad. This is rather intuitive language. However, what is good in one situation may not be good in another. Sometimes you need a problem-solving strategy, and we've seen how poor our abilities to use logic can be. So I'm going to show you that bad decisions are often the result of poor information encoding. Sometimes you don't understand the problem. Some type of bias, a cue overload, which I'll explain, a lack of attention, and other failed cognitive processes. So decision-making doesn't necessarily appear in this order, but it usually involves setting a goal, gathering in some information, structuring your decision, and making a choice. And if any of one of these goes haywire, evaluating the outcome. And if any of these goes haywire, you can go back to a previous stage. So if you discover that you've made a bad choice or the outcome is poor, you can either completely reevaluate your goal or restructure the decision or just remake a new choice. One interesting thing about decision making is there is a mathematical model that should probably be followed. We don't always use those mathematical models. So probability is, of course, the statistical likelihood of a particular outcome. And making decisions involves evaluating the probability of obtaining something that you want, as well as evaluating the value. The problem with decision making is that there are many combinations and things that usually go into making a decision, and each one of these has a particular probability associated with it. Let's say you wanted to buy a car. Well, you consider the price, you consider the style, the color, how large it is, the gas mileage, all of these things factor into the decision, and each factor has a particular probability associated with it. So it's not a simple yes or no, do I buy the car? The best decision involves the probability that the car will break down, the probability that your boyfriend or girlfriend will hate the color of the paint, the probability that it's going to eat a lot of gas on the freeway. And when you add these probabilities together, you get what are called permutations and combinations, various ways that these probabilities add or multiply together. You don't need to know this particular language, but understand the principle behind it. So you might think when you go to buy a car that these things are sort of easy to determine, the probability that you'll like the paint, the probability that it'll get good gas mileage. But it turns out, even when making simple decisions, that there's actually a very complex mathematical formula that should be followed. And as you can see, these formulas are not easy. You don't need to know these. But we're not exactly computing these in our head when we're going to do some simple shopping. We tend to use other heuristics rather than the mathematical probabilities to make our decisions. And there is one mathematical theorem that does sort of show how we make decisions, and it's fairly reliable. It's called Bayes' theorem. And Bayes' theorem, the essence of Bayes' theorem, without getting into the math, simply means that we use our prior experience to compute the possibility of obtaining some future goal or item. And this can be expressed mathematically, but as you've seen so far from what we've studied, the brain is basically a big memory-making machine. So we always have these memories that we're storing, and we use those as means of obtaining future goals. So this is an example. I want to give you a little puzzle, and you can pause it if you don't want to see the answer. But let's say a school has 60% boys and 40% girls as students. Girls wear trousers or skirts in equal numbers. The boys all wear pants. An observer sees a student from a distance wearing trousers. What is the probability that the student is a girl? So if you want to try and solve this, pause it now. Otherwise, I'm just going to go through the explanation. So in order to use Bayes' theorem, you have to know a certain number of things. Remember, we're trying to guess a future answer based on what we know. So we know the event A, that the student is observed as a girl, and the event B, that the student observed is wearing trousers. And this is the formula to compute A in the event of B. So to compute A in the event of B, you need to do all this hard math. Well, some stuff is easy. We know that there's a 0.4, 40% chance that the student is a girl. Easy. We know that the opposite, the complementary to this, the probability that the student is a boy, is 0.6, because those add together to get 1. We also know the probability that the student is wearing trousers given that the student is a girl. This is 50-50, as half wear skirts and half wear pants. The probability that the student is wearing trousers given that the student is a boy is 1. This is easy. Again, all boys wear pants. The probability that a student wearing trousers given that the student is a girl, as they are likely to wear skirts and or trousers, again, is 50-50. This is the opposite of this case above. And now, to compute a difficult thing, the probability of a randomly selected student wearing trousers, regardless of any other information, follows this nasty formula. And you get 0.8. To compute the entire probability that we're looking for, that a student observed is a girl, or that the, what is the probability that the student is a girl, A, given that it's the student is wearing trousers, B. And in order to do that, you need to compute all this probability. You get 0.25. Wow. How many of you are doing that in your head? Not many. But it turns out that people tend to behave very similar to Bayes' theorem in many respects, even though we're probably not specifically calculating that in our head. I'm going to cruise through the Monty Hall problem to show you another difficult mathematics solution. This one we tend to get wrong a lot, and as you know, we did this in lab last week, so you're probably familiar with it. But the general outline of the problem is if I present you with 3 doors, and behind one of the doors is a car, and behind 2 other doors is a goat, what is the best way to make a decision? Most people probably compute some simple math and say that there's a 1 in 3 chance I'm going to get a car. Normally that would be true, but in the Monty Hall problem, there's one twist. When you decide to open up one particular door, let's say you pick door 1, the person who's running the game will open one of the 2 other doors and show you what's behind the other door. And then you have a second possibility to change your decision or stay with the same door. Now, that's where the math gets tricky, because these probabilities between the first round of guessing and the second round of guessing, they multiply. And most people don't see that, so they still perceive that there's a 1 in 3 chance that they win. But that's not the case. They're just not doing the math in their head. The reason this gets the name the Monty Hall problem is a long time ago there was a game show and the host was named Monty Hall, and this is exactly how they ran the game and why most people lost. Sorry, this is all explained in the slides. So the game show host will open one of the 2 remaining doors and present you with a goat. So he'll never show you the car after the first round. He'll show you a goat. And then you have the choice to switch or not. Most people say, is it advantage to change your choice or stick with what you've got? Well, since we've gone through this in the lab, I'm not going to get too far into it. But essentially, if you choose the door that actually had the car behind it, Monty Hall will expose one of the other doors, and the other doors will have a goat. If you switch, you lose with the probability of 1/6 in this case and 1/6 in this case. And switching overall loses with the probability of 1/3. Now, if you accidentally pick a door that had a goat behind it, Monty Hall has to open up the door and show you the other goat. And again, now here, switching loses with a probability of 1/3 in each case. So switching wins with a probability of 2/3 in this case. So after that information and that dizzying explanation, what do you think? What would you do? Again, but the most important part is whether or not you get the math behind that, that we're not computing these probabilities in our head. So we have the illusion. We tend to think that we're making decisions based on the information, reliable information, but we're not always doing that. We tend to use our life experience in decision making, and again, these heuristics are generally helpful, and they can be employed when the stakes are low. It's not a very high risk. You don't have enough time to make a decision, or you can't allocate proper attention to the problem. But it's problematic when you can't accurately relate the past to the present, when you don't have accurate estimations of prior probability, or if it's a very risky decision, you really want to give it all your time and attention. So I'm going to go through a number of heuristics to explain what these are. The first is called the availability heuristic, and this is when you use the most salient example, the most vivid example of your past to guide a decision. The problem is the most salient example is not always the best example. Example, are there more words that have R as the first letter or R as the third letter? Think about how many words you can come up with your head. Now, most people probably say in general that there are more words that start with the letter R than have R as the third letter. They're actually mistaken. The problem is it's really easy to come up with words that start with R, and it's really hard to come up with letters that have R as the third letter. So whatever information is available to you easily, you tend to go with that decision, and it's not always accurate. A similar heuristic is called the representativeness heuristic. Not so easy to say. And what this heuristic states is that we sort of make the assumption sometimes that whatever we're looking at, whatever's right in front of us, is representative of the greater population. So for example, if I look at my classroom of York college students, I might make generalizations about all college students in the world based on the population that I see. But there are students who are very different from all around the world. I might say that in York College, for example, that all psychology students are female because most of the psychology students at York are female. But that might be inaccurate. Maybe there's some place in Western Asia where all the psychology students are male. We don't know. And this is a simple math problem to give you an example of that. So if a cab was involved in a hit-and-run accident at night and two cab companies, a green and a blue, operate in the city, 85% of the cabs in the city are green and 15% are blue. And then a witness identified the cab at the hit and run as blue. The court tested the reliability of the witnesses under the same circumstances that existed on the night of the accident and concluded that the witness correctly identified each one of the colors about 80% of the time and failed 20% of the time. So what you're looking at is you have the total number of cars in the city and the chance that the witness is accurate. So right now, hint, hint, you know that these probabilities probably relate to each other in some complicated way. So what is a probability that the cab involved in the accident was blue rather than green, knowing that this witness identified it as blue? Okay, pause now, and I'm just going to go through the answer if you just want to get to the chase, continue forward. So most subjects, when they're given this example, gave probabilities over 50%, and some gave answers over 80%. There is actually a 12% chance of the witness correctly identifying the blue cab, which is the multiplication of the two probabilities, the number of cabs and the reliability of the witness. And there's a 70% chance, 17, that the witness incorrectly identified the green cab as blue, multiplying the 85% occurrence of those cabs times the probability that the witness made a mistake. So there's a 29% chance, 12 plus 17, the witness will identify the cab as blue by multiplying those or adding those resultant probabilities. Whew, not so easy. Here's what it looks like graphically. Here are the number of cabs. Only 15% blue, 85% green. Here's the probability that the witness was accurate, and here's the probability that they were inaccurate. So maybe this might make a little more sense. But what people see is they tend to see this number correctly identified as being really high, or green as being really high, and they stick with this number here. So they think that this number that we've given is representative of the population when it's not. You can see that there's this huge empty space here corresponding to the points at which the cab is actually green. Yeah, but anyway, the general principle here is that sometimes what's presented in front of us is not always indicative of the population. Similarly, we have what are called framing effects. Sometimes when decisions are influenced by recent history or a person's current state. So if you just got out of a horror movie and you're asked to make a judgment on some faces, whether they're friendly or not, some people might judge some of those faces as less friendly because maybe they got out of a scary movie and they're a little paranoid. And this is sometimes how propaganda works. Propaganda tries to force your decision by constantly bombarding you with a particular message. Same with advertising. Is it McDonald's that says, you deserve a break today? You deserve a break. You should go in and buy yourself some food that's going to make you unhealthy. The general idea is they put their message in a context that biases the way you make a decision. a joke based on this is propaganda. What lies behind us and lies before us are small matters compared to what lies directly in front of our faces, which is often the television set. The television and the media are very influential and very powerful ways of shaping social messages. Anchoring is another heuristic. So what if I asked you the percentage of African nations in the United Nations? Would you say it's higher or lower than 3%? Okay, now hold on to that decision. Would you say it's higher or lower than 65%? Did your numbers go up now that I've changed this sort of parameter? This is the idea of anchoring. Anchoring, if I provide you with some kind of number, it sort of frames your decision making. When I initially introduced this problem as 3%, some of you might have said, well, wow, that's a pretty low number. Maybe there are only a few nations from Africa in the UN. But if I place this with a higher probability, you might say, oh, maybe there's 40%. Maybe it's not as low as 3. People's answer is closer to the anchoring number they're presented with. Do I actually know the African nation percentage? No, I don't. I'm just picking numbers out of a hat. But that's the idea of anchoring, that providing some concrete number can bias your decision making. This is a really important one, sunk costs, otherwise known as effort justification. When you continue to do something because you have already put a lot of effort into it. So for example, let's say you went all the way through medical school, you became a doctor, and then you suddenly decided that you hated it. You hated working with sick people, you hated the hours, there was no justification for doing that job, you never got to see your family. And if that was the case, some people know that and they continue in their work. They worked so hard to get there that they can't give it up, and that's effort justification. Sunk costs occur when you let your efforts guide your decision. Some very unpopular examples of this: the Iraq War, Vietnam War. We kept on pouring more resources into these conflicts because we had already taken it so far. We couldn't just give up. But it's an example of a nation that has sort of fallen victim to effort justification, particularly in the Iraq War, when at some point there was no point for us being over there. So a joke based on that: give up. At some point, hanging in there just makes you look like an even bigger loser. Or stupidity. Quitters never win, winners never quit, but those who never win and never quit are idiots. Know when to fold your cards. Know when to make a new decision or pick a new direction. That doesn't mean quit at every opportunity, but it means don't stick with something just because you've put effort into it. Another heuristic is illusory correlation. See non-existent relationships between two variables when there's no causal relationship. If you've taken statistics, you've learned that correlation does not imply causation. Just because two things happen together at the same time doesn't mean that they're related. And we're really prone to this problem because the brain is essentially a pattern detector. We're designed to detect coincidences. When two things happen at the same time, that's how we learn. That's how a child learns not to put their hand in the fire. It feels pain, it sees the flame, and it makes an association between those two. So this is a huge problem for us. There's also the story of cargo cultists. A cargo cultist, the example of cargo cult is in the islands. This is a purely fictitious story, by the way, but there's the idea that if there are some islanders in the middle of nowhere performing a rain dance, and then suddenly a U.S. cargo plane bringing supplies somewhere else in the world accidentally drops some of its payload onto that island, the natives might think that their rain dance brought about the payload. So now anytime they run out of food, they do the dance, hoping that the payload will come. And that's the idea of being a cargo cultist. Here's another example. So in this graph, sorry, here's my real pointer here. You'll see we have average global temperature increasing over the years from 1820 to the year 2000 in degrees Celsius, and the number of pirates in the world. Back in the 1820s, there were far more pirates. Now there might be 17 recognized pirate associations. So through the years, the number of pirates has gone down and the global temperature has increased. So somebody who falls victim to illusory correlations might say that global warming is caused by a decrease in the number of pirates, and we need to add more pirates to the world. This is, of course, ludicrous, but the idea that there is a real correlation between these two, statistically there's a correlation, but it doesn't mean there's a causal relationship. It doesn't mean these two have anything to do with each other. It's just comedy. Okay, I'm going to stop here for the sake of time, just in case I go over, and we'll continue in part 2.